All right, so we've talked about two measures of dispersion so far. We've talked about variance and standard deviation, and we have the formulae for those here, variance and standard deviation, where the standard deviation is a really straightforward derivative of variance, and I don't mean derivative in the calculus sense, I just mean in the sense that we derived it quickly with the simple square root. Well, standard error is just one more step. So a further derivation of standard deviation gives us standard error, which is denoted this way here. So to get standard error, which has a subscript x bar, so that's our typical way, this x bar that represents the mean of our sample x, the sample mean, we put that as a subscript on the Greek letter sigma. So this is the standard error notation, and we calculate it pretty easily. We take the standard deviation and we divide that value by the square root of n, so however many data points we have in x. So a hands-on code demo to show you how to calculate standard error. So here is that formula. We already have sigma, the numerator in the formula, from the preceding video. So we calculated sigma when we were talking about standard deviation, and that itself calculated from sigma squared, which we calculated in the video before that. So that's variance. We take the square root of variance, that gives us the standard deviation, sigma. And then we can use sigma now divided by the square root of n. So just however many data points we have is n. Take the square root of that, and that is our denominator. So that gives us our standard error of about 0.02. And we don't need to calculate this in so many steps. Like variance and the standard deviation, there are built-in ways in Python that we can calculate the standard error. So the method that we're using here is SEM, standing for standard error of the mean. We pass in our vector of values x, and that gives us a value very close to what we calculated here. So the reason why it's close, but not exactly the same, is because this standard error of the mean method defaults to 1 degree of freedom. So we're going to talk about degrees of freedom later. It's a concept that we don't really need to worry about. I mentioned this earlier with respect to the calculation of variance as well, that with the kinds of larger data sets, if we're talking about dozens, hundreds, thousands, millions of data points, whether we have n or n minus 1 here in the denominator, it doesn't make a big difference to the results. Like this number doesn't vary much from this number. We have to go many decimal points in before we see any change. So yeah, we'll talk about degrees of freedom a bit later again. So this shows you the NumPy library tends to not worry about the n-1 degrees of freedom that statisticians would worry about. And so statisticians, who seem to be more behind the SciPy library that gives us this SEM method, they do worry about having this degree of freedom accounted for properly. But again, with larger data sets like we tend to have in machine learning, doesn't matter very much. If you want to get the exact same value as we had here, then you can set the degrees of freedom equal to 0, and you will get exactly the same value. So what is the value of this standard error? We have a sense of the value of a standard deviation, about how it tells us, how it allows us to plot out and see how much do my data points vary around the mean. Well, standard error allows us to tell whether two different distributions vary significantly from each other, whether it's likely that those two distributions represent two different phenomena. And so distinguishing two distributions in that way using standard error, that's going to be a big focus of the second half of these live lessons when we really start digging into statistics.